Hi everyone, I'm Mohammed Shaz, and on behalf of my group, Celine, Zeroy, Hiroto, and Ihan.
Hi, my name is Saminong Sini.
Hi, my name is Suri.
Hi, my name is Hiroto.
Hi, I am Discrete.
Welcome to our presentation on University Course Enrollment Analysis. In this project, we apply set operations, the inclusion-exclusion principle, and the pigeonhole principle to reveal student enrollment data to uncover scheduling risks that universities face every semester. Here's what we'll be covering today. We'll start with the problem itself, then walk through three core concepts: set operations, inclusion-exclusion principle, and the pigeonhole principle, before moving into our findings, recommendations, and a final reflection on what we learned as a team. Every semester, thousands of students register for multiple modules at once. Tracking who's enrolled where by hand quickly becomes unmanageable. Left unchecked, this risks overcrowding, poor lecturer allocation, and scheduling collapses and resource allocation issues. For this project, we sourced a real dataset from Kaggle to cover three courses: Programming Fundamentals, Database Systems, and Discrete Structures for Scenario 1, and Mathematics 1, Mathematics 2, and Biology for Scenario 2. For the first scenario, we apply two core discrete structures concepts, that is, set operations to map out how enrollments overlap across courses, and the pigeonhole principle. And for scene 2, we use the pigeonhole principle and the inclusion-exclusion principle to check whether tutorial sessions can actually accommodate the number of students assigned to them. I'll now hand it over to Celine to walk through the specific problem we're addressing.
Hello everyone, my name is Celine and I handle the data analysis and set operation. Our project addresses the challenge of managing students enrolled in multiple courses, which can make timetable, planning, and resource allocation more difficult. To analyze this, we module each course as a set of students: course A with 18 students, course B with 14 students, and course C with 10 students. By using the onion operation, we found 38 unique students enrolled across all three courses. And using the intersection operation, we found only a small overlap, which two students are common between courses A and B, two between courses A and C, while courses B and C have no student in common. No student is enrolled in three courses. And using the difference operation, we found that 16 of the 18 students are in course A are not enrolled in course B, showing that most students in course A are exclusive to that course. This results from the basic for the next part of our analysis.
Hi, my name is Hiroto, and today I'll be explaining the mathematical part of our analysis. Specifically, I'll cover the inclusion-exclusion principle and the pigeonhole principle, and show how these concepts help us analyze the enrollment data accurately. First, let me explain the inclusion-exclusion principle. This principle is used to calculate the total number of unique students without counting the same student more than once. If we simply add the number of students in each course, some students who are enrolled in multiple courses will be counted twice. The formula shown on the slide corrects this problem. In our dataset, course A has 18 students, course B has 14 students, and course C has 10 students. There are two students enrolled in both course A and course B. The two students enrolled in both course A and course C, and no student enrolled in both course B and course C. There are also no students enrolled in all three courses. Therefore, we calculate 18 plus 14 plus 10 minus 2 minus 2 minus 0 plus 0, which equals 38. This means there are 38 unique students across the three selected courses. If we have simply added 18, 14, and 10, we all have obtained 42, which is incorrect because 4 students have been counted twice. The inclusion-exclusion principle removes this duplication and gives us the correct result. Next, I'll explain the pigeonhole principle. In this example, we have 38 unique students distributed across 3 courses. When we divide 38 by 3, we get approximately 12.67. Since the number of students must be a whole number, we round up to 13. According to Pigeonhole Principle, at least one course must have at least uh, 13 students. Look at the actual enrollment numbers. Course 41 has 18 students. Course 5 has 14 students. And course 44 has 10 students. Therefore, course 48 and 41 and course 5 both satisfy this mathematical guarantee. These calculations show that our data is mathematically consistent, and these principles can help university plan timetables and allocate resources more effectively. Thank you for listening. Now I hand over to the next presenter, who will explain our finding and recommendation based on this result. Thank you.
Hi, my name is Zuri, and I translated this calculation into practical insight. First, even though most students in our data set takes only one courses and meaningful share, 4 students takes 2 or more at once, meaning courses can be timetabled in isolation. Second, course A, programming fundamentals, is the biggest overlap, which it share more common student with the other 2 courses than they share with each other. This means PF timetabling should be prioritized first to avoid cascading conflicts. Third, the pigeonhole principle proves overlapping enrollment is mathematically unavoidable. Whenever courses registration outnumber unique students, this is certainly not just something we observe. Based on this, we recommend university schedule programming fundamentals separately from the other 2 courses and automatically flag multi-course students so their session never clash.
Hi, I am Iftikhar. Today I explain the conclusion part in this project. This project showed that discrete mathematics can be used to solve real university problems. By using different mathematical methods, we analyzed student enrollment data and found useful information for planning classes and schedules. After these slides, the next slide is reflections. Our team worked together to complete this project successfully. We share our tasks, communicate regularly, and check our work carefully. This project improve our teamwork and understanding of the topic. The next slide is reference. We use several discrete mathematics book and Kaggle datasets to complete this project. This source helps us understand the concept and perform the analyzing correctly. The next slide is sources. Thank you for listening to our presentation. We hope this presentation helpful. You understand the practical use of discrete mathematics. Thank you.